Compared with even a decade ago, automotive engineers have substantially more steel grades to select from in their quest to balance properties, performance, manufacturability, sustainability, and cost. Today, we'll be discussing how some of these latest grades are applied in body structures to address specific formability problems. This blog and others are featured on AHSSinsights.org, the leading online resource for technical information on the forming, joining, and metallurgy of advanced high-strength steels for automotive applications. This information is made available by World Auto Steel, the automotive group of the World Steel Association. I'm Danny Schaeffler, President of Engineering Quality Solutions, and I'm also the technical editor for Metallurgy and Forming of the AHSS Application Guidelines. Since the 1980s, high-strength low-alloy, or HSLA, steels have been used with great success in automotive applications. Development of advanced high-strength steels like dual-phase, complex-phase, and more recently, the family of third-generation advanced high-strength steels was spurred on by the need to have additional ductility at even higher strength levels. Conventional dual-phase steels with a microstructure of simply ferrite and martensite have excellent formability in the drawing and stretching deformation modes. However, the characteristics of this phase combination that work very well in these deformation modes lead to challenges in bending and edge stretch deformation. Complex phase steels have superior performance in bending and edge stretch deformation, but are not as good as comparable strength dual phase steels when it comes to drawing and stretching. Third generation advanced high strength steels are a family of grades that combine the best features of the other steels while minimizing some of their associated limitations. However, the same techniques and approaches successfully deployed to form parts from high-strength low-alloy steels may not be appropriate for the characteristics of these advanced grades. As an example, B-pillars are a particularly challenging part for cold stamping applications. The upper section must be of sufficiently high strength to prevent cabin intrusion during a side impact, while the lower section needs to maintain at least moderate ductility to absorb crash energy. Production manufacturing constraints dictate that the blank edges are usually formed by mechanical shearing rather than by laser cutting, and forming the targeted part shape puts these cut edges in tension, exposing the risk for edge cracks in these higher strength steels. This combination of these challenges contributes to many OEMs choosing to form B-pillars and even entire door rings using hot stamping of press-hardened steels. With new types of advanced high-strength steels now commercially available globally, cold stamping approaches can again be considered. Metal flow, when forming shear-cut blanks into B-pillar upper shapes, put the cut edges into tension along the front and rear door opening regions adjacent to the B-pillar, as highlighted in the dash box. Edge cracks propagate into the part is frequently the outcome. The difficulties faced by metal forming simulation packages in predicting the risk of cut edge cracking makes this all the more challenging, since the simulation may give the false impression that there is no cracking or splitting concerns in this area. Blank design countermeasures accomplish only so much. Meeting this challenge, the steel industry now offers options at the same tensile strength, but have nearly twice the cut-edge ductility as measured by the hole expansion test. With this alternate grade, the same part and process design is now capable of achieving the targeted part dimensions and characteristics. OEMs usually design B-pillar lowers with the intention of having these sections capable of absorbing side impact crash energy before the passenger cage intrusion is stopped by the higher strength B-pillar upper. Implementing this strategy usually means that the B-pillar lower uses a combination of thinner gauge and lower strength than the B-pillar upper section. Vehicle stiffness must be maintained, so the lower horizontal portion highlighted may have a relatively deep draw depth, which is also needed to accommodate the contours of the rocker shape. From a formability perspective, the deep draws and aggressive designs put these stampings at risk of splits due to insufficient elongation and end value. However, after changing the grade to a third-generation steel of the same strength, but with greater elongation and end value, no issues were found when stamping this deep-drawn part design. For additional examples on other parts and guidance on aligning your grade selection to the needs of the part, please visit the AHSSinsights.org website and look for the Case Studies page within the Steel Grades tab under Metallurgy. Here, you'll also find the links to the original studies where the images and details came from. But for now, that wraps up our video blog. Visit AHSSinsights.org to learn more about advanced high-strength steels. If you're watching this on YouTube, please subscribe and give us a like. We'll be doing more of these videos in the future. I'm Danny Schaeffler with Engineering Quality Solutions. To learn more about the services we provide relative to sheet metal forming, troubleshooting, or training, please visit eqsgroup.com. Thanks for watching, and have a great day.